This video shows a comparison between a very good AD converter and a, let's say, normal AD converter. The samples are fed directly into the computer, and these are fairly fast converters. One is the PCIe 9842. I start that with its icon first, and I go through the setup procedure, even though I have done that before, but that's just to show how it is set up. So that is U, and then A to select something, and I select PCIe, that is K, and then I set the rate dividend to 1. That means the card will send samples at a rate of 200 megahertz into the computer. Frequency error is unknown, I put 0 there. Then Linrad cannot handle 200 megahertz. I put 3 here. 2 to power 3, that is 8. So Linrad will take the average of the samples in groups of 8. And that results in a sampling speed of 25 megahertz. And that's the about maximum that this computer can manage. Since each sample is the average of 8 samples, the signal to noise ratio is improved. It works like the samples are 14-bit, but by making the average of 8 samples, it behaves as a 15.5-bit AD converter. And that's it. X. And do not forget to save. That's always so in Linrad. That is because you might want to make some tests, and if they fail, it's nice to have the old parameters still in the files. I'm going to use this for AM later on, so I press F for AM mode. And here we are, and here is a signal. And for some odd reason, Linrad now uses more CPU resources than it did when I tried it just a couple of minutes ago. You see 100% here. I don't know why that is, but this is Windows XP and it behaves like this occasionally. I just press escape. And here is a bug that I will have to correct. I don't know the reason for this. Windows XP is now a bit old, and I solved it this time by starting another program and then exit, and now I go back to the PCIe 9842 and press F and click on the signal, and it didn't work, so don't send, and then start bladeRF and run it, that's F, and start PCIe 9842 and press F, and then click on the signal, and now it works at 95% CPU load. I don't know the reason for this. It happens occasionally with Windows XP. It's how the scheduler puts the program on different cores, or how memory is allocated or something. I don't know. But it's a very high CPU load for a single thread. The average load, there are many cores in the processors here, so the average load is low. And then I go through the setup for the bladeRF, X, U, and A. And bladeRF is J. And input this through the j61 connector. So it's yes. And sampling speed, that is 40 megahertz. And Linrod cannot do 40 megahertz. It cannot even do 20 because this is 2 channels. So I have to put 2 here. That will give 10 megahertz and that will be okay. Error unknown. And then XX and save. Not really necessary because I saved an identical setup recently. F, and here we are. And I click on the signal I have here. And this is a 2-channel receiver. It is the blue track that is the track we look at. This is the signal source, 1 megahertz minus 60 dBm. I have set the calibration, that's the number here and here, to have the S meter to show minus 60 dBm. Of course, it's not a correct calibration because the signal is split on the 2 receivers just by connecting them in parallel. But it's convenient for what I'm doing now. So I switch off the signal generator. And you can see that the level goes down by 35 dB or 37 maybe. So the noise figure is just a little better for the PCIe here. The difference is very small, not significant. So now switch it on again and increase the signal level in steps by 10 decibels. Oops, here the bladeRF saturates. This is about 1 dB below saturation and it is 0 on the signal generator and of course it's 0 on the S meter graph as well. I continue to increase the level. Oops, that's not so easy because the generator stops at plus 10. I have to go to 1 dB steps. And I make a 10 dB step back from here. No, that's not going to be correct because the generator says plus 17, but it doesn't go that high. Anyway, we see there are nonlinearities. I press A to see the amplitude margin, and you can see here it's 0. So it is saturated. Now I am 1 dB below saturation. The level on the signal generator is 12 dBm. Means the dynamic range is 12 dB plus the difference in noise floor, maybe 13 or 14 decibels. That's the difference between the bladeRF 12 bits at 40 megahertz and the PCIe 9842 with 14 bits at 200 megahertz, which corresponds to 15 bits at 50 megahertz. 15 as compared to 12, that is 3 bit, should be 18 dB, but I only see 12 dB. I don't know the reason for this, but of course the noise floor is not only the ideal noise floor. There are contributions from the input amplifiers and things that I don't know so much about. Anyway, there is a difference, but not very dramatic. As it turns out, there is a far bigger difference in real life when I connect these receivers to an antenna. This is something I have to do in daytime, because at night the differences are much smaller. It is 1:30 in the morning. I have connected a whip antenna and tuned the bladeRF as well as the PCIe to 252 kilohertz, where there is a BBC station, I think. I'm not so sure, but it's British anyway. And on the bladeRF it sounds like this. Means more or less perfect. And on the PCIe it's very much the same. So at night I don't see any significant difference between these radios. Could be the presence of carriers in a quiet region like here, let's say 0.5 megahertz. And let's say, you see there are carriers here, and I go to 0.5 megahertz here and look at it. And there are fewer carriers here. So this better, far more expensive AD converter is more linear than the bladeRF. To what extent that matters has to be demonstrated in daylight. Now it is in the middle of the day, 1 o'clock. The long wave stations are weak and the medium wave is more or less absent totally. I'm listening on the PCIe 9842 and I can hear there is an English voice, but it's not easy to hear what the lady is saying. Now I switch to the bladeRF, click down that and click up this. And here is something odd. There's N being said in CW. It's the local non-directional beacon, and you can see when it transmits the noise floor goes down very clearly. We can see it on the S-meter graph as well, of course. What is very odd is I have only one channel connected, but the beacon is in both channels. If I listen to the other channel, it is far worse. This is an AD converter, and I think this is a sign on digital feedback. That means the digital data enters the input of the AD converter. I will now switch to connect the antenna to this channel instead. And as you can hear, the NDB is not present here. I go back to the PCIe. And again here. It sounds like this bladeRF is a little bit better. It means lower noise figure than the PCIe, while the other channel is the other way around. Now the antenna is into one channel and I'm listening on the other channel. I will remove the AGC to make it more clear what one is hearing, like that. Now I will disconnect the antenna and insert an amplifier. And you can see there was about 10 dB of noise increase in this channel to which the antenna was not connected, while the noise increase was a little bit higher to the other channel. So I listened to the other channel. And use the AGC again. And there is a characteristic noise that is related to interference inside the AD converter. I switch off the bladeRF and listen to the PCIe 9842. And it doesn't have this kind of interference. So there is a big difference between these two receivers. Now I connected the antenna to the other input of the bladeRF. And here you can hear it sounds nice. So one of the channels is clearly not really good. The other seems to be fully adequate for it's quite clear that it is much better to connect the antenna to this input and probably best to not use the other one at all. It would be advantageous, of course, to have a second antenna and to use Linerad's automatic combination of antennas, but since the noise floor is so much higher in the other channel, and since that noise leaks into this channel, it's better to not.
Starting today with Get and our assessment to the
Now it is 5:30 in the afternoon. I'm listening to PCIe 9842 on 252 kilohertz, and it sounds nice. So I go to the bladeRF, and it does not sound very good. You can hear the voice, but interference dominates. This is the carrier of BBC, and here are interfering false carriers. If I listen on the other channel, you can see the signal level differs by about 15 dB. We can hear the local NDB a little. I will now switch the signal to the other input. And it's rather similar. And then if I listen to the channel where the antenna is not connected, we hear the NDB again. To understand what's going on, it will be necessary to do measurements and to feed signals in a more controlled way into the bladeRF. These tests were with an amplifier. I will remove the amplifier now. And then I listen to the other channel. And just so you remember, I go back to the PCIe 9842. You can see the amplifier made the signal levels much lower. And the signal is now too weak. It's no longer easy to hear what this voice is saying. I can hear it faintly in the noise. Now I am feeding two signals into the bladeRF as well as into the PCIe 9842. The signal level is high, and although we can see there are some more false signals in the bladeRF than there are in the PCIe, it doesn't look alarming. But the crucial thing is not what happens at high signal level, it's what happens at lower levels. The generators are both set to -10 dBm, and I will step them down now in steps of 10 dB. Now it is -20, and what we see here didn't get much better. I mean, if you take the ratio of the signal and this false thing, the signal goes down, but the false signal does not, at least not much. I will lower the signal levels one more step. And you see the false signal stays while the real signals go down 10 dB each time. So I go on. -40 dBm, and you see now false signals here are only 10, 20, 30 decibels below the real signals. 30 decibels is not much. This is the explanation why there was a lot of interference. And I continue to make the signal weaker. And This one is still very strong, and there are many false signals. There are false signals here as well, of course. And that's rather interesting. At some particular signal level, it's now minus 60 for both generators. Now it's minus 50, and you can see how much higher the noise floor became. Look here, 8 decibels or something like that. Maybe less, 6, 7 perhaps. And I continue and increase the signal level again. And you see all the false signals become strong, but the noise became lower. So it's quite clear that the bladeRF AD converter is not suitable to use as a medium wave receiver, or as a receiver at all, presumably, because although it can sample at 40 megahertz and give us 20 megahertz bandwidth, the performance is mediocre. Here is the bladeRF. It's inside a box to avoid pickup of interference. Here is the inside. This is a ground point, grounded here, and here is another ground point, grounded here. The midpoint, the ground point here is grounded there, and the two inputs for the two channels are here, and they are fed from the toroids. It's necessary to add a DC voltage on the center top of the windings on the toroids, and that's done with this potentiometer that gets its well decoupled supply voltage from this connector here.